Hi everyone and welcome back to PrepFusion. I'm Anish and today we will start with the new chapter of network theory, that is network theorems for AC circuits. So you have learned from Himanshu about network theorems for DC circuits. So today we will discuss the same for AC circuits. Mostly it will be similar, but the complexity will come because I can have supply or source of two different frequencies. Then the complexity increases. Otherwise mostly things will be same and the maximum power transfer obviously will change here. Okay, it will not be same as RL equals to RTH, it will be something else. So we will discuss about superposition theorem, source transformation, Thevenin's Norton's theorem, maximum power transfer theorem. All these theorems we will discuss. Reciprocity theorem is the same, right? It does not change obviously. So before going into the superposition theorem, we have to understand linearity. Linearity in AC circuits combines homogeneity and superposition. So basically for a circuit to be linear, okay, it has to follow the principle of homogeneity and superposition. And we know RLC, all these elements are linear in nature. All these elements are linear in nature. Okay, so remember this thing, RLC are all linear in nature, but your input signal must have the same frequency. Why? Because I know my element like R is not a function of omega, right? R is independent, the resistor is independent of omega, but L and C are functions of omega. Okay, so you have to be careful here, because if your frequency changes, right, your impedance will change, right? Then everything will change, current, voltage, everything will change. So what do I mean by this? Let's take a very simple example. Okay, let's take a very simple example. So if I have a circuit somewhat like this, right? So this will be register and register. Okay, and this is the output, this is the current that I am measuring, right, IT, and this is the input voltage. R is let's say 1 ohm, and 1 ohm is there. Okay, and input is sin t. Okay, so what will be the current? Basically current will be sin t by 2. This is my current. Now if I change this circuit, right, so let me just get back to this example. So now if I change the voltage, basically if I copy the circuit and I just double the voltage, the current will also get doubled. That is what this homogeneity means. If the input magnitude changes, the output changes proportionally without affecting the phase. Okay, so that is what homogeneity means. So if I double it, current also will be what? Current will be I 2 sin t divided by 2. Okay, so yeah, that is the current, and this is the current here, this is the current here. Current basically doubles. Okay, so current basically doubles. Now what we can do is, let's take another example where the circuit is containing inductor or capacitor. Let's take inductor only. So L is 1 Henry and this is 1 ohm. Okay, and again my source is sin of t. So now what will be the current? So if I write the current, right, it will be voltage sin of t, or I can assume my sin of t to be the reference 1 angle 0 divided by the magnitude of the impedance, that is 1 plus j omega. Omega is 1, so it will be 1 plus j omega. So it will be 1 by under root 2 angle minus 45. Okay, so basically, right, if I convert it back, this will be 1 under root 2 sine of omega or sine of t minus 45 degrees. Okay, now what I can say is, if I double the supply voltage, basically what will happen? This will just get multiplied by 2. Ultimately this will be under root 2. So the homogeneity principle is following. The homogeneity principle is following. So like I will just not write it, I will just directly copy and paste. Basically if I double the supply, what will happen? Everything will be doubled, correct? Magnitude will be doubled. So here the magnitude will be doubled. this will be double, this will be 2, this will be 2 by root 2, this will be 2 by root 2. It will be just doubled. Now one thing I change. Let's say from the sin t only, I change something else. I change the frequency. So if I change the frequency and then double, it will not just simply double, right? If I change the frequency here, let's say I change the frequency to 2t and then I double it. Will it be same as this one of simply doubling? No. Why? Because this one will change, right? This imaginary component, the inductor will change. It is depending upon the frequency. So it is omega into L. So omega is 2 in this case, so it will be J2. Okay, it will be J2. Now this will be under root 5 and the top also will be 2 only, this will be 2 only. So it is something else, right? And angle is also, I don't know what is the angle. Angle is something theta. Okay, I don't care about the angle for now, minus theta. Okay, so the thing is, it will not hold. The homogeneity will not hold if the frequency has changed. So please keep this in mind whenever we are talking about these principles, right? Frequency must be same, okay, for same kind of response. We will discuss for different frequencies as well. So that is what is the solution? What is the solution? Solution is superposition. So the superposition is the response due to multiple inputs is the sum of individual responses caused by each input independently. So what you will do is, I have a source sine of t. For this I will get some frequency component, this, right? Where did it go? This one. Then again I will have another source sine 2 of t. For this I will get some current. Okay, so individually I can add them. So individually this is the source due to which I am getting this current. Remember, sorry, this is not t, this will be 2t, right? Because here the frequency was 2t. So due to this source the current will be this, due to this source the current will be this. I can individually add if I am having two sources, okay, of different frequencies. I can individually add those things. Okay, that is what superposition tells. The response due to multiple inputs is the sum of individual responses caused by each input. So of course we will see a question through there also, we will basically understand this. So from this basic example I hope you have understood. So one more thing, if I would have changed the phase here, right? Let's say the phase here, this would have been changed to this phase. If I would have changed to sine t plus 45 degrees, you can verify by yourself what will happen. Just another extra 45 degrees will be added, so ultimately this will be 0. Okay, so the linearity holds, the homogeneity holds. Whatever phase change I will do, same phase change will be coming at the response as well. Okay, whatever magnitude change I will do, same magnitude change will be coming at the response. So ultimately, right, this homogeneity basically means if I have initially some magnitude v1 and some phase theta 1, and then if I change, and for this the response is, let me write this properly. So let's assume this to be some v in and theta. Just hold on, this, let me set it to log, let me unlock it. Yeah, so if this is v in theta in, what I can comment, what I can say is that for this I am getting a response, let's say magnitude of v out and theta out. Okay, now let's say I have multiplied the response with a factor of alpha and I have changed the phase with plus beta. So the response also will be changed alpha times magnitude of beta into theta out plus beta. I hope you are able to see here, theta out plus beta. So the important point is, what is the important point? Again, remember what information is not present in this phasor representation? Frequency. So assumption is, of course, you are discussing about the same frequency component. If you discuss about the different frequency component, then this will not be valid. Okay, Just be careful. For different frequency component, first you have to write this relation, then again you can do the same thing. Okay, so assumption is these are for the same frequency component, same frequency component. Okay, so that is the case over here. So what now, like, what is the superposition? Superposition is basically, if I have two sources, let's say this one source is, this was the homogeneity principle. If I have two sources, right, one source is V in 1 angle theta 1, another source, right, the frequency can be different. Okay, so I will write here V in 1 sine omega 1t plus theta 1, another source is there plus V into sine of omega 2 t plus theta 1. Okay, so individually if I just find out the responses for each of these sources, right, the response is somewhat like this. For this first one, it is V out 1 sine of omega 1 t plus theta, not plus theta, okay, V out plus theta dash 1. Okay, so because the phase obviously will be different than the input, depends on the circuit elements, and here it will be V out 2 sine of omega 2 to omega 2t theta 2 dash. Okay, so individually the responses are this. So if I combine the two inputs, okay, if I send the input together, okay, my input is this V in 1 sine omega 1 t plus theta 1 plus V into sine omega 2 t plus theta. Okay, this will be, sorry, this will be theta 2, right, this will not be theta 1 plus theta 2. This, right, response to this will be combination of both of these, right? So it is same. I can just copy and paste basically. Okay, combination, right, it will be combination of these two. That is what superposition means. So this you have already learned. Same follows for AC. Just one thing you have to keep in mind, that I cannot simply write them together. I have to write them separately because there are two different frequencies. Okay, that is the only difference that you have to understand. Okay, so remember one thing, that if you are applying the theorem, make sure your load is also linear, right? If your load is non-linear, then these theorems won't be applicable. So make sure your load is also linear. Okay, so yeah, that was about the superposition and linearity. So let's, like, this is the homework for you. This I want you to do. You have to find out the amplitude of V of t. If amplitude of input is double along with a phase lead of 150 degrees. So if I have added a phase lead of 150 degrees to the input, and obviously I have doubled the input amplitude, what will be the output V of t? What will be the V of t? So for this input, the V of t is given. Okay, if I make some changes, what will be the V of t? That is the homework for you. Okay, this is the homework task for you, that all these questions I will solve in the next lecture. Okay, now let's move on to the, like this superposition theorem, right, what I was explaining, that the superposition theorem states that in a linear AC circuit with multiple independent sources, the total response voltage or current will be algebraic sum of all the responses. Actually this is not correct, it will be the phasor sum, right? Algebraic sum also you can say, yeah, algebraic sum you can say, algebraic sum caused by the each source acting along while other source is replaced by internal impedance. So like this you already know, we can use it, right? It is mainly used for multi-tone signals. So what I will do, I have to find out this I2 current. So first I will make I can convert this circuit, right, in two cases. So first case will be where my this one will be gone. Okay, so this one will be totally gone. So if this is totally gone, it will be replaced with its own internal impedance, whatever is the internal impedance. Let's assume its internal impedance is ZB. I hope you know how to replace a voltage source with its internal impedance. And now if I find out the current, right, current will be some this I2 dash. So I2 dash will be the function of only VA, okay, due to the input VA. Now next modification what I will do is I will make the other source to be 0. I will make this source to be 0, right? If I make this source to be 0, let's assume its internal impedance is ZA. So if its internal impedance is ZA, then what will happen is, then what will be the uh, current I2 double dash will be only function of VB. What I can say is my overall current I2 due to all the sources, both the sources, right? If both the sources are active, the overall current I2 will be equals to I2 will be equals to what? I2 dash plus I2 double dash. This will be the overall current. So same as previous case only. Okay, and remember, if they are of same frequency, simply you can club them together. If they are orthogonal, you can add their powers. Okay, so if I2 and I2 dash are orthogonal, then individual powers can be added. Powers can be added. Okay, so we can do this. Obviously, if they are orthogonal, we can add the individual powers. So now let's okay, so yeah, this is the homework. I wanted to give you homework because these are very simple questions, so which we will solve in the next lecture. So you try to calculate the value of VO with help of superposition theorem. Okay, so first you calculate the value of VO for this source with making this source inactive, then you calculate the value of VO making those source active and this one inactive. Okay, so from there you will proceed. Let's now move on to the case, very interesting case. So these questions are very interesting, which I will solve. Like this one is very basic. I think you will be able to solve it. You will be able to solve it. If you are not able to, of course, I will solve in the next lecture. So let's see this question. So here there are two cases. Case one is when the power consumed by the load is this one actually. This is the load basically. Power consumed by the load. Okay, power consumed by the load is 20 watts. It is given that the power delivered by the voltage source is twice the power delivered by the current source. So I know the power delivered by the voltage source is twice the power delivered by the current source. So let's assume the voltage source delivers some power PV, okay, and the current source delivers some power PI. So this relationship is there that the voltage source, the power, it is given that the power delivered by the voltage source is twice that the power delivered by the current source. Okay, 2 pi. And you have to find the power consumed in case 2. Okay, so what is the power consumed in case 1? I know PV is equals to 2 pi. Okay, and I observe that the frequency components are different. So my voltage and current signals are orthogonal. Also, one thing you have to keep in mind, your load is purely resistive. So this is a very good thing, because if your frequency is changing, right, the load impedance could have also changed. But as the load is purely resistive, so it does not matter what is the frequency, my load resistance will not change. So R will be constant, RL will be equals to 2 ohms. This will be constant. Okay, so RL is equals to 2 ohms. Now let's discuss uh, as voltage and current signals are orthogonal and the load impedance is not changing, the power, right, can be simply added. So I know PV plus 2pi, PV is equals to 2pi, and the total power consumed is 20 watts. The power consumed by the load is 20 watts, and I know that the powers can be added because the signals are orthogonal. As the signals are orthogonal, that's why I can add the power. Why? Very basic thing is that, what is power? Power is, in a resistor, it is IRMS whole square into R. So how do you find out IRMS? So what is my overall I? Overall I is I dash of t plus I double dash of t. So let's assume this I dash of t is due to the voltage source whose frequency is 2 radian per second, and let's assume this I double dash of t is due to the current source whose frequency is, sorry, this is the voltage source, right, whose frequency is 3, and due to the current source this is the 2 radian per second. Now what you can do is, as these two signals are orthogonal, what will be the RMS? RMS will be what? IRMS will be under root of, I hope you know this, right? This we have learned in the power chapter. I hope you have not forgotten this yet. Under root of IRMS dash whole square plus I double dash RMS whole square. Okay. So if I square this, right, so what is my IRMS? Overall IRMS whole square. Overall IRMS whole square is I dash RMS whole square plus I double dash RMS whole square. Now if I put this value here, it will be what? It will be equals to I dash RMS whole square into R plus I double dash RMS whole square into R. So basically what is this? This is the power due to the voltage source, this is the power due to the current source. So simply it will be equals to PV and PI. So now I hope you, like, I am able to prove it to you that we can simply add the powers because signals are orthogonal, because the RMS value is just the under root of that formula, right? So it will be PV plus PI is 20 watts, and I know PV equals to 2 PI. So basically it changes to 3 PI equals to 20 watts. So PI equals to 20 by 3, that is 6.67 watts. Okay, and what is your PV? PV will be twice of this, so it will be 6.67, so 40 by 3. 40 by 3 I think is somewhat 13 point something, right? 6.67 into 2, 13.34 watts. Okay, so PV and PI is this value. Now what we can comment is that yeah, PV PI we have got. So what next they are asking? They are asking the power consumed in the case 2. So in the case 2, right, if I observe the voltage signal, the magnitude has changed by thrice and the phase shift there is a phase lag of 30 degrees, and here as well the magnitude has been halved and there is a phase lead of plus 75 degrees. But of course for power, right, we only care about the magnitude because IRMS only depends on the magnitude, amplitude, not on the phase. Okay, so in the other case, what will happen is that so in this case, what is the I dash RMS? So in the first case, if I find out, I know my I dash RMS whole square into R equals to 6 point, no, not 6.6, sorry, it is due to the voltage source, right? Voltage source is 13.34. So from here my R is 2 ohms, right? So I dash RMS due to the voltage source, I can find out is 13.34 divided by 2, it will be 6.67. What about same for I double dash RMS? I double dash RMS will be, okay, sorry, there is a under root also, right? Sorry, there is a under root also. So I have to do the under root also. So if I do the under root, it will be 2.58, 583 amperes. Okay, what about I double dash RMS? Again, if I find out I double dash RMS, it will be 6.67 divided by 2. Then if I do whole under root, it will be 1.8 to 826 basically. Okay, so this is the I double dash RMS. Now I have observed that basically I only care about the magnitude. So the voltage source is getting multiplied thrice. So my I dash RMS as my V is getting 3V. So I dash RMS, I only care about the magnitude, I don't care about the phase. So the I dash RMS will be what? I dash RMS will become 3 times the previous value, that is 3 times 2.583. So 2.583 into 3. So this is equals to 7.49 amperes. Okay, and what about the I double dash RMS? For I double dash RMS, my input, right, this is my V in is getting changed, and my IN is getting changed to half, right? It is getting halved. So it is simply getting halved. Amplitude is getting halved. So if amplitude is getting halved, this will be 1 by 2 IN. So my I double dash RMS will be 1 by 2 into the previous I double dash RMS, that is 1.826. So 1.826 divided by 2, this will be 0.913 amperes. Okay, now you find out the powers basically. So power, new power, right? New power will be again I1 dash new whole square into R plus I1 double dash new, of course these are in RMS, whole square into R. So basically it becomes this whole square plus 7.749 whole square into 2. So comes out around 121.76 watts. Okay, so you could have solved this in a shorter manner as well. Okay, you could have solved this in a shorter manner as well. How you could have solved it? So basically, right, so this part, right, this part is like you cannot reduce this further. So for like this is the method 1 with basics, everything I explained from scratch. Method 2 is, if I copy this, right, I will apply the same thing only, but it just in a bit faster manner. So method 2 is here. So what we observe is that the overall power is 20 watts and the PV is twice the PI, and I know this is a purely resistive circuit and I know these are orthogonal. So definitely I will directly write here that P overall power will be equals to PV plus PI, that is PI is 2 PV, sorry, PV is 2 PI, so it will be 3 PI. So 3 PI is equals to P, 3 PI is equals to P. P is P is how much? P is 20 watts, right? They have told me in the question P is 20 watts. So PI will be 20 by 3, so 6.67. Okay, and PV will be 13.33. Now next you observe that the voltage source is getting thrice, the amplitude is 3 times. So how much will the power increase? Power will increase by 9 times, because amplitude is getting 3 times, that means RMS value will also increase 3 times. And what is power? Power is RMS whole square into resistor. So voltage is getting 3V, so my voltage square, because I am only concerned about the RMS, right, RMS whole square, so V square will be 9V in square basically. So power will be 9 times, so power PV will be 9 times PV. So if I multiply 9 here, this is what, 40 by 9, right? If I multiply 9, this will be 120. So your PV new will be 120, and your current is getting reduced to half in amplitude. So how much power will get reduced? So same thing, right? If current is current by 2, then current square will be current square by 4. So basically your PI will become PI by 4. Okay, so PI is 6.67, so 6.67 divided by 4, so your PI new will be 6.67 divided by 4, so 6.4, so it is 1.6675 watts. Okay, so plus 120, so this will be your power will be 121.667 watts. Okay, so this is your power basically. Same we got in the this result as well, right? So like this is the shortcut and that was the long cut basically, but with that you understood each and everything, right? So basically power is proportional to the square of the current, that's why power is getting reduced or increased more. Okay, so basic thing that you should keep in mind is that if I have a voltage signal that is getting multiplied by n, so your power due to this voltage signal, right, power due to the voltage signal will be n square of the previous power. That is what you have to keep in mind. Power will be n squared. Same for current, same for the any other source. Okay, and you can only add the powers if they are orthogonal to each other. So that to explain you that concept, we have taken a bit of example, right? This superposition theorem again in a better manner. So here I have a input voltage source Vs of t and current source. So the response is given as this. Okay, now response is given as this. Now can you tell me, if the input is this and this, if it is changed to this and this, then what will be the response? Very easy, right? It is very easy, because you can easily map the 3t component with 3t component and 2t component with the 2t component, because these are mappable. So I can directly say 3t will map to 3t and 2t will map to 2t. Okay, so what is the factor here? So by how much I am changing? I am multiplying by 3. I am multiplying by 3 and changing the phase. I am adding a phase lead of 60. I am multiplying by 3 and adding a phase lead of 60. Same will occur to the corresponding response. So I have to multiply by 3, multiply by 3, and add a phase lead. How much phase lead is this? Plus 60, right? So I will add a phase lead of 90 degrees. Okay, plus what about this one, right? This one, the amplitude is reduced to half, phase lead is plus 90. So amplitude is halved here, so amplitude will be here also, it will be half, and I have to add a phase lead of plus 90. So it will be 100 and plus 98, so it will be 105. So this will be sine of 2t plus 105 degrees. Okay, what about this one? Can I comment about this one? For this I can say what is the output. For this is possible, right? Output of this one is possible, but what about this one? I cannot say what is the response of this particular signal. Why? Because the frequency is t, right? I only know the response for same frequency components, for omega equals to 3 and omega equals to 2. I don't know the response for omega equals to 1. I don't have a reference equation, right? So I will not be able to solve. I will not be able to solve this one. Okay, this is not solvable. So only this response I will know, this response I will know, but this one I will not know. Okay, this one I will not know. Let's solve for another case. If I have a voltage and current source, and now if they are of same frequency, if I have a voltage and current source, if they are of same frequency, yeah, sorry for the interruption, just I had an important call to take. So here we have this, right? So these are all same frequency components. So of course, due to this voltage source, I will get some voltage that will have a frequency of t. Due to this current source as well, I will get some voltage which will have frequency of t. And just in case if both of them have same phase, then they will be clubbed together. I cannot comment. I cannot comment. Or even if they have different phase, then also I cannot say due to which one I am getting the source, right? So basically what I mean by this is, let's say this is 10 sin t plus 30 degrees, and due to the current source I am getting something 5 cos t, 5 cos t minus 15 degrees. Okay, so but I don't know, both of these are like frequency components of 1 radian per second, right? So I don't know whether this response is due to this one or is due to this one. I don't know. Can you tell me? If I don't tell you, you will not be able to find out until and unless you know about the network, inside the network, right? Until and unless you know about the network, you will not be able to comment due to which I am getting the response. If I tell you due to the current source I am getting this response, due to the voltage source I am getting this response, then you can calculate. But unless and until I tell you, you will not be able to find it out. So what you will require, you will need two equations. So in this case, we will need two equations. Okay, so yeah, that is what I will tell you. So unless and until I tell you due to which response this is, you will not be able to find it out. So now if I change this, right, if I, let's say if this is minus 60, right, and if I assume the response is due to this one, so this is minus 60, this is plus 60, so this one will be also plus 60, so this one will be cos of t plus 45 and of course the response, if this is made thrice, right, so this will be thrice 15 plus this is halved, this will be 5 sine t plus 120. So if I give you these two equations, now you will be able to say, because you will notice, what you will notice that what is the phase difference here, 60. So which of the following sinusoid has a phase difference of 60 from point 1 to point 2, okay, from case 1 to case 2. So if you observe, this one has a phase shift of plus 90, this one has a phase shift of plus 60. So you will say, sir, then that means this is the response due to the voltage source. So you can directly say, if I have given you two equations, you can say this is the response due to the voltage source Vs of t, and this is the response. Of course, if you see the what is the phase shift here, 90, and the phase shift here is 90. Also you can verify with the amplitude as well, right? Here the amplitude is halving, here also amplitude is halving, here the amplitude is getting thrice, amplitude is getting thrice. So I hope you get the point. If I have same frequency components, I will need two equations. One equation will not cut it. Okay. So now can you tell me what will be the response due to this one, if the voltage source is changed to this and the current source is changed to this? Of course, now you can tell, right? If I have given you these two equations, now you can simply tell, because this is the response due to the voltage source. So this is the response due to the voltage source. So voltage source is getting divided by 5. So this one will also be getting divided by 5. This will be cos of t cos of t. And what about the phase? So the phase right, phase will be here phase has changed to plus 75, right? Phase has changed to plus 75, so this will be plus 75. Okay, and for this current source, the amplitude has 2 by 3, the factor is 2 by 3, right? So it will be 2 by 3 factor, so this will be 20 by 3. Okay, and I may correct here, this is getting halved. Okay, this is being thrice. Sorry, it is not 2 by 3, sorry, it is 3 by 2, right? It is 3 by 2, so 3 by 2 is just like 15, 3 by 2 will be 15, right? What is the factor here? Factor is 3 by 2, factor is 3 by 2, sorry. So this will be sine of t. What is the phase shift here? Phase shift is again plus 75, phase shift is again plus 75, so this also will be plus 75, that is 105 degrees. Okay, so like this you can solve, and trust me, one day GATE will frame a question. Until now they have never asked a question like this in AC, but I am totally like 100% sure in the future, right, they will ask a question from this particular topic, because this is neither calculative, there is no calculation involved, but trickiness is there, right? So GATE examiners do love these kind of questions where there is a bit of trick but calculation is not there. Okay, so yeah, that is what you have to keep in mind. So like superposition theorem, right? How do you solve the superposition theorem? Just this is the superposition theorem. This whatever you have learned is the superposition theorem basically. Whatever you have learned is the superposition theorem, that's it. Okay, nothing else. So just find out the phase and angle and then add. Also, if you want to solve this, right, you can find the angles as like you can find the quantities. So what do I mean? So if you want to see the mathematical approach, so this was the simple basic approach, fundamental approach. Mathematical approach, if you want to see, we can discuss about the mathematical approach as well. Okay, so what is the mathematical approach? All of these are in the same frequency component, so I can use phasors here. So if I use phasors, so let me assume that my sine of t to be the reference. Okay, this is the reference. So sine of t is equals to what? Sine of t equals to 1 angle 0. Sine of t is 1 angle 0. So what is the phasor of this? This will be 5 minus 30 plus this will be what? This is what? Cos of t minus 45, right? So what is cos t? Cos t is sin 90 plus t. So this will be sin of t plus 45. So this will be 2 plus 45. Okay, I have just changed the cos to sin, cos to sin. What is this? This is 10 sin t plus 30. So this will be 10 angle 30 plus this will be 5 t minus 15, but if I change this back to sine, this will be 75. So this will be 5 angle 75. Okay, this is the first equation basically. So in normal DC, if you remember, you used to write this A into some input voltage, then B into some input current is equals to my first equation. This you used to write as your first equation, but the difference was it was a scalar quantity. It was a scalar quantity. This A and B are at that point of time was a scalar quantity. What is the second equation? Second equation is this one, right? Second equation is this one. So this will be A times 15 angle 30, 15 angle 30 plus B times 1 angle plus 45. Okay, so this will be equals to what? 5 angle 120 and 15 angle 15 angle, this is plus 90, right? So this will be plus 125. 15 angle plus 125, 135. This is the equation 2. So this is similar to the superposition theorem. So I am not explaining how am I writing this. I hope superposition theorem you have already studied. For DC, something similar I am doing here. Okay, this is just a revision. The important fact to note here is your A and B are complex quantities. Complex quantity. So what you will do, the homework, what is the homework for you? Homework for you is solve, find out the values of A and B. Solve A and B. Okay. Now after solving A and B, now if the source has changed to this, right, sin t plus 45, so it is put in this equation 1 into plus 45 degree into A plus this one is 3 plus 120, right, 3 angle 120 into B. Okay, and of course you know what is your A, you know what is your B, right, because you have solved A and B. It will, all of these will be some magnitude of A, theta A, and this will be magnitude of B, theta B. Okay, so ultimately from here you will, you know A, you know B, you know this values, so ultimately you will get some result. Okay, this will be an answer. So this is what I wanted to do and cross verify. Okay, so that's why, right, of course this seems a bit difficult because complex quantities are here. So the first method is really simple. Okay, just by observing the sinusoid you can directly do it without doing anything. Okay, but here you have to solve for A, right, and those will come complex quantities that will be a bit difficult. Okay, so you can do, this will be homework for you, you can try it out. Okay, so this is the method 2 basically, the mathematical way of superposition theorem. So mathematically superposition theorem means this, and visually I have explained, right, exactly what does each source response mean. Okay, so remember this method is valid only when frequency is same. Method is valid only when frequency is same. Okay, otherwise it is not valid. Just be careful regarding that. Okay, So yeah, that was basically about the superposition theorem. I hope you have understood. Like, trust me, this, right, this concept, no other educator in this simple manner, like most of the educators don't teach this, okay, I know this, and whoever teaches this, they won't teach you this simplified example, right? They will not teach you this simplified example, okay? It will be a bit complex. So trust me, whatever you know the best content, you have the best content. So whatever you are watching, whatever you are learning, right, you are learning from the best resource. That is my guarantee. Okay, so let's now move on to the next theorem, that is source transformation. Very similar to our, like what do you say, our normal source transformation in DC. So a voltage source can be converted into a current source with a parallel uh, source impedance, and a current source can be converted into a voltage source with a series source impedance. Very same, just the difference is here the source impedance will be complex and the voltage can also be sinusoidal. That is the only difference, except that everything is ditto same carbon copy. Everything is ditto same carbon copy. There is literally zero difference. That is about the source transformation. So now let's discuss about the Thevenin's and Norton's theorem. So in Thevenin's and Norton's theorem, so Thevenin's theorem is basically same for DC and AC. Just you need to keep in mind that the circuit must be linear. So circuit must be linear, then only you will be able to apply the Thevenin's theorem. Okay, and the load also must be linear if you want to apply the Thevenin's theorem on the whole circuit. If you want to just apply on the circuit except the load, then of course the load can be linear, non-linear, it does not matter. Okay, so make sure the circuit is a linear circuit, then only the Thevenin's theorem and Norton's theorem can be applied. I am not explaining you what is Thevenin's theorem, what is Norton's theorem. This you have already learned previously, right? That's why I am not explaining you. Also keep in mind, these theorems are only valid for single frequency components. Single frequency components. Okay, so basically what I can comment is, if I have like two different frequencies, right, and I have to solve for current and voltage, then for multi-tone signals, that is multiple signals with different frequencies, for multi-tone signals we have to solve individually. Okay, that is the only thing that you have to keep in mind. For multi-tone signals we have to solve independently. Why? Because I hope you understand your impedance will be a function of omega, because resistance is not a function of omega, but your capacitive reactance and inductive reactance are function of omega. XL equals to omega L, XC equals to 1 by omega C. So if your omega changes, the impedance will change, the Thevenin's impedance will change, the open circuit voltage will also change. So that's why you will find out the individual open circuit voltage, individual Thevenin's impedance, and for that particular frequency you will find out the current, and ultimately you will repeat this process for the different frequency components, and at the end you will just write the overall result using superposition theorem. So multi-tone signal means basically I will apply the superposition theorem. Apply superposition theorem. Okay, so that is what you have to keep in mind basically here. But just also keep in mind that like sometimes, right, if you have already, like I think Himanshu has already mentioned that your thumb sometimes, if it is purely resistive, your RTH, the Thevenin's resistance, can be negative. Why it can be negative? If the network contains, if network contains dependent sources. Okay, so this thing you have to keep in mind basically. So like few homeworks I will give you. So this is the first question that I wanted to give you. Find the Thevenin's equivalent voltage across AB. So I think you will be able to solve it. I don't feel this will be that much difficult to you. Okay, this is the homework for you. Very basic exercise to get you started with. Okay, now let's come to another question. This is a very interesting question. Let's solve this question. So here we have been asked if the load impedance is given by ZL equals to Z star. Okay, what is Z star? ZTH star. What is star? Star basically means the conjugate. I hope you remember, right? Star basically means the conjugate. So whatever is the Thevenin's impedance, the load impedance is the conjugate of the Thevenin's impedance. So what is my Thevenin's impedance then? So if the load is conjugate, my Thevenin's impedance will be the conjugate of this one load impedance. So it will be 2 minus J3. So this is my Thevenin's impedance for this particular network. Okay, fine. And the power consumed by the load is 100 watts. So the power consumed by the load is 100 watts. If it is 100 watts, right, what is it equals to? It is equals to IL RMS whole square into R, because of course power is consumed only in the resistive part, it is not consumed in the inductive or the capacitive reactance. If supply voltage is changed to Vs of t 150 sin 10t plus 60, if the supply voltage Vs of t is changed to 150 sin of 10t, okay, initially what was the supply voltage? It was 100 sin omega t minus 30. If it is changed to, yeah, one thing I forgot to mention this, right, this frequency is not omega, I'm sorry, this frequency will be 10. T. Okay, this is what I forgot to mention. So these are the same frequency. So now everything is sorted. So important point is, you know the Thevenin impedance, okay, and they are telling you this is the new load impedance and this is the new supply, then what will be the power consumed by the load. Okay, so how do I find it out? So right, I don't even need the previous power consumed actually. So I know this is my supply, new supply is what, 150 sin 10t plus 60, 150 sin 10t plus 60, and your Thevenin impedance, you can replace this whole network with a Thevenin impedance and an open circuit voltage. Okay, you have to replace this whole network with a Thevenin impedance and open circuit voltage. Okay, what is the open circuit voltage here? So yeah, we will actually require the information about the power. I'm sorry, we will actually require the information about the power because I need to find out the Thevenin voltage, right? So the power is 100 watts. So from here I will be able to find out the IL RMS square into R. So IL square RMS into R, this will be what? IL RMS will be what? Will be, R is how much? R is, load is 2 ohms, right? Resistance is 2 ohms and power is 100, so it is 50 under root. Okay, 50 under root. So this will be, if I take the 50 under root, this will be 7.07 amperes. Now I can replace my equivalent circuit. I can replace my equivalent circuit with VTH. This will be my VTH and this will be my ZTH, and this will be my ZL. Okay, remember, like I have to assume a reference, so my reference is sine 10t. This is my reference. Okay, I know the current through this circuit. What is the current? Current is like the RMS magnitude of the current, I magnitude IL magnitude is 7.07 amperes. Okay, and I know ZTH is equals to Z like ZL equals to ZTH whole conjugate. So this is 2 minus J3. My ZTH is 2 minus J3 and ZL is 2 plus J3. So basically, right, it behaves as a purely resistive circuit. So overall Z, right, what is the overall current I? Overall current I will be equals to VTH divided by ZTH plus ZL. So in this case, like they are opposite, the imaginary components are opposite, so it will be equals to what is VTH? VTH is equals to my, I don't know what is VTH, okay, I don't know, but I do know what is I. I is magnitude of I is 7.07. So but what is the phase of the I? Phase current, I don't know what is the phase of the current. Okay, so the phase of the current I don't know. Okay, this is 10 angle 30, right? Okay, this is the magnitude. Okay, they are only asking us about the power consumption. So actually I will not require the phase. I will explain what do I mean by it. I will explain what do I mean by it. So here my current I will be equals to, yeah, sorry for the interruption. Basically, like, people really shout a lot, so I have to turn the noise off for a certain seconds. So here I was explaining we will not require the phase. I will discuss why we will not require the phase. So let's assume that VTH has some angle theta TH. Okay, so the what will be the angle of I? Angle of I also will be theta TH only, because this is totally real, right? So this will be VTH divided by theta TH divided by the ZTH plus ZL, that is 4. So this is a real quantity, right? So it will not change the phase angle. So I will be equals to, so basically my magnitude of VTH will be equals to what? Magnitude of VTH will be magnitude of I into 4, and assumption is I am discussing about RMS. So everything is RMS here. This is RMS. Okay. So I have already calculated the RMS value of load current, that is 7.07. So this will be 4 times 7.07. So if I multiply 4 times 7.07, it will be 28.28 volts. 28.28 volts. Okay. So that is what my VTH is. Now let us do the same for like this is my VTH, right? This is my VTH and my circuit is totally linear. And overall, what is the VTH? Overall the VTH is angle magnitude of VTH angle theta TH. I don't know what is theta TH. Okay, so this will be 28.28 angle theta TH. I don't know what is theta TH. Now if I have changed my supply to 150 angle of 10 sine of t plus 60, what will be the VTH change to? So VTH also, how much have I multiplied the amplitude? Amplitude has been multiplied 1.5 times. So the VTH also will get multiplied this amplitude by 1.5 times. Why? Because it follows the linearity principle, because it consists of only RLC elements. So it will also follow the linearity principle. So this will be my new VTH. New circuit will be like this: VTH dash, okay, angle of, I don't care, theta TH plus, of course, how much phase difference is there. So previously it was minus 30, now it is plus 60. So I have added 90 degrees. So here also the phase will be shifted by 90 degrees, but you will observe it does not matter, because I am concerned about magnitude. I am not concerned about the angle, because I have to calculate the power. So if I have to calculate the power, I am not concerned about magnitude. I am only concerned about the power, right? Only concerned about the power. So this will be ZTH. ZTH will not change for this network, right? ZTH will not change. ZTH is from the previous case only, as frequency is constant. Frequency has not changed, so ZTH also will not change, because the imaginary component could have changed if the frequency would have changed. But here frequency is same, so the imaginary component will be same. So ZTH is 2 minus J3. So here ZTH will be 2 minus J3, and I will write here as frequency is same, ZTH will not change. Okay, so ZTH will be here, and they have changed the load now. So the load resistance ZL is equals to load resistance ZL. So load resistance ZL equals to 1 plus J1. Load resistance ZL equals to 1 plus J1. Okay, 1 plus J1. And just hold on, I will check if computer is really warm. Okay, 1 plus J1. And what I can say is my so from here I will be able to find out the current, right? What is current? Current will be this VTH dash theta TH, angle of theta TH, plus 90 divided by the whole magnitude, right? Divided by the ZTH plus ZL. So, but what am I concerned? I am concerned only about the magnitude. I don't care what is the phase or something. I don't care about the phase, right? I am concerned only about the magnitude. So if I am concerned only about the magnitude, what will happen here? So basically my magnitude of current will be magnitude of this VTH, that is VTH only, magnitude of this whole thing, that is VTH dash, okay, divide by magnitude of ZTH plus ZL. Okay, so this magnitude of VTH I have already discussed, that magnitude of VTH will be 1.5 times this. I have not written it, unfortunately. Okay, I have written it, right? So this is the new VTH, right? Okay, no, I have not. So it is 1.5 times this, right? 1.5 times this, so it will be 1.5 times this, that is 42.46. so magnitude of VTH dash equals to 42.426 volts. Okay, so this will be 42 point, this is the magnitude, right? 42.426 divide by magnitude of this. So this is 2 3 and this is minus 2, so 3 J2 3 J2 3 J2. Okay, so magnitude of this. So because, right, for power what do I need? For power I just need magnitude of IRMS, and remember everything was in RMS, so this also will be in RMS. Everything was in RMS previously, that was my assumption. So this also will be RMS, I square RMS into R, right? So for that I just need the magnitude of current, I don't care about the phase. So the magnitude, this will be, right, 3 square plus 2 square, that is 9 plus 4, that is 13 under root. So 13 under root, then if I multiply 42.426, this will be 11.767 amperes. Okay, so basically what I have to do, I have to okay, have I done it correctly? I guess I have, I guess most probably I have. I will just quickly verify this, right? 42.426 divided by 13 under root, yes, this is correct. And this 11.767 into resistance is how much? Resistance is 1 in this case, resistance is 1, so it will be 11.767 watt only. Okay, so this is a very beautiful question. So you did not require any complex calculations here, but still there were so many concepts involved here, right? So that is the beauty of this question. So yeah, this will be the answer of this question. So just, if you are not able to understand, please go through it again, so that this will be more clearer to you. Okay, now let's discuss about the maximum power transfer theorem. Basically in maximum power transfer theorem there are many cases, so we will solve each case one by one. So let's start with the first case. If both my reactance, this is not XL inductive reactance, right? This is my load reactance. I don't know whether the reactance is capacitive or inductive. This is my load reactance and this is my load resistance, where both are varying. Both load reactance and load resistance both are varying. So what I can say is, if you remember in maximum power transfer theorem for DC circuit, you used to differentiate the current with respect to resistance, but here both are varying. So with respect to whom I will differentiate, that I have to figure out. correct, with respect to whom I will differentiate. But first let's write the expression for for the power across the load. So what is the power across the load? The power across the load is magnitude of I whole square into RL, because only the power is consumed by the only the resistance and not the reactance. So what is the magnitude of I? Magnitude of I is voltage V in, magnitude of V in divided by, this is just a series circuit, right? So it will be Zs, it will be Zs plus Zl, okay, Zs plus Zl. So magnitude of V in into Zs plus Zl. So this will be what is magnitude of V in? Magnitude of V in I don't know. Obviously it is a constant number, right? V in is not varying. Okay, sorry, this is the current whole square into the resistance RL. Okay, and I can replace my Zs and Zl with respect to their equivalent values. Zs is Rs plus jXs, the source reactance, and this is RL plus jXl. So ultimately this will become V in magnitude of Rs plus RL plus j xs plus xl. Okay, so yeah, that's it basically. Into RL is of course there, right? What is the magnitude? This magnitude of V in is just V in, correct? It will not change. This whole square is there, so this will be V in squared, and this magnitude will be under root Rs plus RL whole square plus XS plus XL whole square, correct? If I square that, automatically the under root sign will go away, so this will be Rs plus RL whole square plus XS plus XL whole square into RL is of course there. That is my power. Now what we will do, we will first differentiate with respect to XL. So we will first see the condition for XL with respect to XL, then I will differentiate with respect to RL, and there is a reason. The reason I will explain. I will explain the reason. Okay. So first, because here two things are varying, right? So first I will change this, then I will change this. Reason I will just explain in a second. Okay. So let me differentiate this expression with respect to PL divided by DXL and equate it with 0 for maximum power transfer, because then only PL will be maximum, right? If the differentiation of this is maximum, either I will get maxima or minima. In this case it will be maxima. Okay. So if I differentiate this, V in square is obviously constant, right? So V in square, okay, this whole numerator is constant, so only denominator is the one that is changing. So this will be minus V in square cannot come outside, V in square into RL can be outside. This will be minus 1 divided by Rs plus RL whole square plus XS plus XL whole square raised to power minus 1, obviously, n into n minus 1. So this will be raised to power minus 2, and of course chain rule is in action, so I have to differentiate the inside function as well. So differentiation of the inside function will be, this is just a constant, I will treat this as constant because I am differentiating with respect to XL. So this is constant for me. The differentiation here will be simply 1, or not 1, sorry, 2 into, this will be 2 into XS plus XL, okay, equals to 0. Now of course this whole thing can never be 0. V in is not 0, RL is also not 0. So what can go 0? This can go 0, right? So from here we get the first condition. This is my XS plus XL is 0. XS plus XL equals to 0. So my XL basically is XL is minus XS. Okay, XL is minus XS. So this is the condition 1. This is not the total condition. This is the condition 1. And intuitively can we understand this? There are two conditions here. This is the first condition. Intuitively can we understand this? Intuitively this makes sense. Why it makes sense? Because if you see one thing, that this is my equivalent circuit. Now mainly, right, what does power depend on? One is on RL, another one is on the magnitude of current I. Okay, so what is I? I is Vin upon Zs plus Zl. So I have to, like, Vn is constant, so I have to minimize this Zs plus Zl. So of course resistance can never be negative. I cannot have a negative resistance unless and until it is an active circuit. So somehow I have to cancel this reactance. If I cancel this reactance, the impedance, right, overall impedance will be lower. Same thing we have learned for resonance as well. In resonance also, the reactance cancellation happens. There it was basically the capacitive reactance and the inductive reactance. Here I don't know what kind of reactance it is, but whatever it is, if I connect an opposite reactance at the load, and if it cancels out, ultimately, right, the impedance has been reduced. And if the impedance reduces, the current increases. And if the current increases, the power increases. So ultimately, what is your aim? Like intuitively, how you can understand that you have to reduce your ZL. Okay, if ZL reduces, your current will increase, and if current increases, your power will also increase. Ultimate aim is to have maximum power transfer, and all of, like, none of the power is getting consumed by this reactance, right, by this load reactance. All of the power is consumed by the resistance. So that is our primary focus. So our primary focus is on the resistance and on the current. Okay, so this is the first condition. So first condition is this, you have to satisfy this one first, then you come back to the second condition. Second condition is what? Now what I will do, now put this condition. Now put XL equals to minus XS in, let me write this equation 1 or something, that will be better. Yeah, in this equation 1. Okay, so if I put this in equation 1, okay, so from here my PL power will be what? Of course the reactance will get cancelled. I will be only left with V in square into RL divided by RS plus RL whole square. That's it. Now again you differentiate this. Okay, now if I differentiate, again the same condition, right, it is just like a DC. It is same like the DC case, right? If I differentiate this with respect to my resistance, load resistance RL, which is varying, so it will be equals to, now this one is interesting. So V in square is outside, it is just a constant. This will be RS plus RL whole raised to power 4 into 1 into RS plus RL whole square minus 2 RS plus RL into, okay, yeah, into RL only. This is my equation where I have to equate this with 0 for maximum power transfer. So if I equate this with 0 like this, I think you have already learned with Himanshu. So this will be RS plus RL can get cancelled, because my assumption is RS plus RL is not equal to 0. Why? Because RL has to be positive, right? RL is positive. That is why it is not equal to 0. So I can simply cancel this one out. I can divide by RS plus RL on both sides. If I divide by RS plus RL on both sides, this will be RS plus RL minus 2 RL equals to 0. So ultimately you get your result, that is RL equals to RS. So of course this is the familiar equation that you know from the DC circuits, correct? So this is the condition 2, right? First what you have to do, you have to make the reactance 0 so that the current is maximum, then you put RL equals to RS. So from this the condition has been derived that the load impedance must be the conjugate of the source impedance, okay, that is equals to RS minus J XS, okay. So from this the condition came, right? I know you know this famous condition. Now what if I tell you that you cannot vary the XL? What if I tell you you cannot vary the XL, you can only vary the load resistance, you cannot vary the load load reactance, you can only vary the resistance? Then right, you have to assume XL plus XS to be constant, then you have to directly solve. So if I just assume my RL is varying, XL is not varying, XL is fixed, that is the only option. So again I will write the whole formula. So formula, this first things will be same only, this much will be same, this much will not change, right? This much will be same. So this much will be same. After this now I will differentiate from the starting itself with respect to RL, because my XL is constant, okay. So my XL is constant, so I can directly write with respect to, like, V in square is constant, right? So V in square will come outside, okay, and this will be in the bottom RS plus RL whole square plus XL whole square, okay, and this whole square, right, denominator whole square, then differentiation of the numerator, this is 1 and the denominator will be copied as it is, RS plus RL whole square, okay, into XS plus XL whole square and minus the differentiation of the denominator, that is XL is constant, right? So that will not vary, RS plus RL into 1, this will be 1 only, into the numerator, basically numerator is RL only, numerator is RL only, okay. So this I can do with a square bracket, this I have to equate this with equal to 0, right? So ultimately this one should go to 0. So here things will be a bit different, okay. So RS plus RL, can I cancel out? Okay, RL is here, I cannot simply cancel out RS plus RL, okay, yeah, this one will go away automatically. So yeah, this one, right, if we XS plus XL is there, whole square is there, okay. So now if I, like, rearrange the terms here, V in square will go away, so this will be RS square plus RL square plus 2 RS plus RL, RS plus RL, RS into RL plus XS whole square plus XL whole square to XS plus XL, okay, minus 2 RS plus RL plus RL whole square. Obviously 2 is also there, right? 2 is also there. So 2 is also there. Okay. So this RS plus RL and plus RS plus RL will get cancelled out. This RL square will go here. This RS square will stay here. This will be still XS plus XL whole square, right? This can still be XS plus XL whole square. So this will be RS square plus XS plus XL whole square equals to RL square basically. So ultimately your RL, right? I will ignore the negative solution because RL is a positive number. Assumption is it is a passive load. So it will be RS whole square plus XS plus XL whole square. So this is a very good formula. It's good if you can remember, right? What is it? It is basically equals to what? It is basically the magnitude of the XS plus XL, the reactances plus RS whole square. And of course, if let's say it is capacitive and if this is inductive, then there will be a minus sign here. I hope you understand, right? You have to take into account the phase. You have to take into account the phase. Okay, so make sure that you take into account the phase. So sign will be according, not phase, sorry, sign will be according to the type of reactance, according to capacitive or capacitive kappa, okay, or inductive, okay, capacitive or inductive. And this is the basically the part where my load reactance is varying. So I will just put here dot j. My load reactance is varying here, only varying the XL. So if I only vary the XL, right, as solved from the first case, it will follow the same, right? My XL will be equals to minus XS. So this will be whole totally copied. Okay, there will not be any change because I have already done it, right? In the first case I have already solved for it. So of course I don't need to repeat myself, right? I hope you understand this thing. I hope I don't need to repeat myself. So let me copy the, where is the condition? This is the condition, right? So there is only one condition because your XS is simply same, so you don't need to worry about that. Where did it go? Yeah, here. Sorry, your RL is constant, so you don't need to worry about RL. Just you need to vary your XL. So of course it will be maximum when your reactants are cancelling each other out. So current will be maximum then. Current will be maximum then because your RS is fixed. So these are the all conditions that we have derived, right? So this is a very good table. This you can either use as a short notes to remember things, or put in your short notes, whatever you want to do, okay, or keep it as full notes only. That's also fine. Okay, so these are all the tables basically. Here I have RL plus JXL. If only RL is varying and everything is constant, then the load resistance must be the magnitude of RS plus XS plus XL, where sign you have to take into factor the sign. Okay, you have to take into account the sign. Okay, then RL plus JXL, of course the reactants must cancel each other out. If both are varying, impedance will be complex conjugate. Okay, if only RL is varying, again if only RL is there, there is no reactance. So here, right, you will just put here in this formula, just remember this formula is the main formula. Okay, and just in this formula, right, put XL equal to 0, you will get back to this result. So this formula is derived from the previous one. Same for this one as well, whereby both my XS, XL both are 0. So automatically your RL will be equals to RS. So this formula is the main formula, and here I have XL but XS is not there. So again we are deriving from this formula only. You just put XS equals to 0, you will get back to this result. Okay, same formula. Now you might have a doubt, sir, why is not there a purely reactive load? Okay, so I will write here, what about purely reactive load? What if I have a purely reactive load, then what will be the condition for maximum power transfer? So basically I hope you remember that in a purely reactive load, because we have talked about all the cases but we have not talked about the case that is purely reactive. Why? Because power is only consumed in resistance, right? It is not consumed in reactive loads. So that's why, of course, we don't discuss about the case of purely reactive load. So yeah, these were all the cases basically. I hope you remember. Sometimes it is lagging a bit, I don't know. I feel sometimes it is lagging. Okay, that's fine. So yeah, I hope you have understood this point. Now another case is, let's say we have not discussed for the case where my source is purely reactive. What if my source is purely reactive? What if my source is purely reactive? Then what will happen? So then what you have to do is, okay, I think it is lagging due to, I got it, due to the fan noise. Okay, got it. That is why it is lagging. We have to turn on the fan. Okay, not the fan, basically my CPU is lagging right now. I think I need to buy a new system. So here what I can say is that you can apply the same formula. What formula? If your ZL is equals to RL plus JXL, simply what you will do for maximum power transfer, right? Again, you have to cancel out the reactance. So you will make XL equals to minus XS, so that the reactance part is gone. So no reactance, then your current will be maximum, impedance will be minimum, hence your current will be maximum, and if current is maximum, your power will be maximum. So we have discussed for this case as well. So I will write here, if my source has only JXS and both my load resistance and my load reactance is varying. Okay, so this will be RL equals to under root RL equals to, not under root, sorry, RL equals to any value. For any value of RL, any value, it will always be maximum power transfer. I will explain what do I mean by that. I will explain, but the condition being that your XL is equals to minus XS. Basically, right, what is your current? Your current equals to V in upon Z, right, magnitude of Z. So it is equals to V in upon magnitude of Z. So V in is V in only, V in upon magnitude of Z. Okay, V in upon magnitude of Z. Magnitude of Z is, if I assume my XL equal to minus XS, so it will be R V in upon R L whole square, not whole square, V in upon R. And what is the current? Basically current, right? What is the power? Sorry, what is the power? So this is the current, right? Because what is the impedance? Impedance is, as XL is equals to minus XS basically, right? My impedance is R plus total impedance is R plus XL plus XS, JXL plus XS. So if these are negative of each other, so ultimately it becomes Z equals to RL only. Okay, so your input current is Vn by RL. So now what is the power expression? Power expression is magnitude of I whole square into RL. Okay, so this will be equals to V in square by RL basically. So now if I differentiate this with respect to RL, so let me differentiate this with respect to RL. DPL by DRL. Okay, so it will be minus V in square divided by RL whole square. So and I have to equate this with 0. So when will this equation go to 0? At RL tending to infinity. So basically, right, this does not have any maxima or minima. No maxima. Why no maxima? Because RL equals to infinity is not a valid solution. And I hope you understand V in square by RL equals to infinity. No, this should not be Okay, no, it should be RL equal to 0. Okay, something I'm doing wrong, right? No, I square into RL V square by L. Yeah, I'm not doing anything wrong. Basically, you cannot put infinity here, right? If you put infinity here, this will be 0. That is not possible, obviously. Either this will go 0 at infinity or 0, RL equal to 0, right? Like what do I mean? Basically, this graph, right, does not have any maxima or minima, because what is the graph? If you plot the graph, right, of RL with respect to RL of PL, it is just inversely proportional, right? Vn is constant, so basically my PL is inversely proportional to RL. So the graph will be somewhat like this. Graph will be somewhat like this. Okay, so of course this graph, right, does not have a maxima, right? This graph does not have a maxima. Okay, so we cannot certainly say for what value of RL it will be maximum. If you choose 1 ohm, it will be some power value. It will, if you choose 2 ohm, it will be higher. Okay, not 2 ohm. Sorry, if you choose even lower values, it will be even higher. Okay, so you keep on choosing lower values and it will be more and more higher. But I can never touch the maxima of this graph, because maxima does not exist for this graph. This graph is not continuous. Got it? So these kind of questions can also be framed. So I am giving you a few homeworks. This is the first question, and obviously previous questions are obviously there. I'm sorry if it is very slow. Okay, this is the next question, and this is the next question. I think that's, yeah, this is the last question, and with this we will solve all these questions in the next lecture, and also I will solve few extra questions. I hope you have enjoyed this lecture. If you did, make sure to like and comment down below which part you enjoyed the most, and I will see you in the next lecture. Until then, happy learning.